All right, here we go. I'd like to click them all close, please. Put all phones away, etc. Did you want to go over there? You can.
No, because I can't see as well.
Oh, okay, there you go. Gotcha. Okay, so we want to just wrap this up. You should have a chance to do some work on the assignment. Test is coming up next Monday or Tuesday. I'll let you know by the end of the week which day it is, Monday or Tuesday of next week.
Not Wednesday.
No, not Wednesday. Monday or Tuesday. Okay, so let's here's where we left off. Let's take a look. We did one yesterday where it was already factored for us, right? And we wanted to find the zeros, and then we actually used that information to sketch this graph, right? We found that there were the zeros of the function. When we talk about zeros, identify the zeros. That just means where is our function equal to 0, right? And so we're just applying the zero product property, and the product of the factors is equal to 0 only when individual factors are equal to 0, right? You can only get products to equal 0 when you multiply by 0. So either this factor had to equal 0, which happens when x is -7. This factor had to equal 0, which happens when x is -1/2. Or this factor had to equal 0, which happens when x is +4, right? And based on the multiplicity of those zeros, that tells us the nature of the x-intercepts, okay? Because the multiplicity of the red 0 was 1, that factor was to the first power. That means that it's going to act like a linear polynomial, and it's going to cut like a line. It's going to cut through the x-axis like a line. Because the multiplicity of the 0 at -7 was 2, it's going to act like a quadratic polynomial. It's going to look like a parabola, and it's going to bounce off the x-axis, right? And then finally, the 0 at x equals 4, that one had a multiplicity of 3, so it's going to cut through the x-axis like a cubic function does, right? That's one that looks like that, right? Where it's going to come down and graze the x-axis and then cross it, right? Okay? And when we put all that stuff together, that's the picture that we had. If we combine that with the end behavior, right? If we look at this function, to know the end behavior, I just have to determine what is the leading term, right? And what would I get there if I did that? I would end up with an x squared from that first part, right? If I square out x plus 7, I get x squared plus a bunch of stuff times 2x times, what about this one? If I cube out x minus 4, I'm going to get x cubed plus a bunch of other garbage, right? So I end up with an x squared times an x cubed is x to the 5th times 2x is 2x to the 6th plus a bunch of other stuff that we don't care about because we only want end behavior. End behavior always comes from the leading term in the polynomial. So that looks like an even, a positive even end behavior, which is this, right? Positive even. So I know it's going up at both ends. And then in between, it just has to do all the stuff that we said on the previous page. It was going to bounce at -7, cut like a line at -1/2, cut like a cubic at +4. So that's the picture we get. Pretty amazing, right? That we can do that. Okay, so let's go back and let's try this for a function that's not factored. So what do we have to do then? We got to factor it, yeah. So again, we just want to know where is this thing equal to 0. But in order to find out, we have to be able to apply the zero product property. So we've got to factor. So what can I do first? Okay, factor out an x squared. Good. And what's that leaving behind if I do that? -8, okay. And then let's see, okay. What does that factor into? So I can break that apart. What magic numbers multiply to -8 and add to -2? Okay. So I'm getting, let's do this the other way. So I get x minus 4, x minus 4 times, you said x plus 2. Okay, and if all those are equal to 0, what does that give me for my zeros? What's the 0 of the red factor going to be? 0. Okay, whoops. And what's the multiplicity of that one going to be? 2. Okay, what's that mean it's going to do? Going to bounce, yeah. Going to bounce like a parabola, isn't it? Okay. What's another one? -2. Okay, so we get a 0 at -2. That's our green one. What's the multiplicity? 1. So it's going to cut like a line. Good. And the last one? Multiplicity. So it cuts like a line also, right? Okay, so now let's get a sketch of this thing. Okay. Okay, so now how about our end behavior? Well, that's kind of nice that we don't have to do anything now because we can just see the polynomial. We can see the leading term. Yeah, so we got positive even behavior, right? So we know we're getting this. End behavior is that, right? And then all we have to do is combine our end behavior with the types of x-intercepts we have, and we got it. Well, first of all, let's add our x-intercepts in there. We had a green x-intercept at -2. We had a red x-intercept at 0. And we had a blue x-intercept at +1. Okay, and we know our end behavior is rising to the left and to the right. Okay, so if I start at the left, and we said we were cutting like a line at the green x-intercept, then doesn't that mean we're doing that? What did we do at red? We bounced, and then we cut, right? So that's our function, what it looks like. Okay, has to. Okay. Okay, how about this guy? What's the end behavior going to be? Okay, if we were going to multiply this whole thing out, yeah, we got a 2. And then if I take that piece right there and I expand it out, what's it going to look like? What's the leading term going to be? X squared. Okay, how about, let's see, let's pick a different one. Let's go gray. How about that one? That's just x squared, isn't it? If I multiply all that stuff out, what do I get for my leading term? 2x to the 4th. So that's telling me my end behavior is positive even, right? Good. Okay, so which one? A, B, C, or D? C? Is that what I heard? Third one down? Yep. I like it. That works. Okay, what are the x-intercepts? Okay, now to find the x-intercepts, there's a couple Couple ways I could do this. I mean, I could just set those factors equal to 0 and solve. But if I want to use multiplicities, I'd have to keep going with those a little bit. Okay. So I've got my 2, and then I've got my factor x minus 2 squared. What does x squared minus 9 factor into? X, well, okay, so x minus 3 times x plus 3 is just difference of squares, right? X squared minus 3 squared. Okay, and if we're finding zeros, then what would my x-intercepts be? 2, 3, and negative 3. Yeah. Now, do you see we could have gotten that from here also? I could have just said, okay, x minus 2 is 0 when x is 2. X squared minus 9, that factor is 0 when x squared minus 9 equals 0. And if I were just going to solve that, wouldn't I just get x squared equals 9? So x equals plus or minus 3, solving by square rooting. Agreed? How could I know that the multiplicity of each of those was 1? Okay, good, because when I factor this out, the exponent up there was 1, wasn't it? Right? And I split into 2 separate zeros from that, and so each of them only gets a multiplicity of 1. We could kind of reason through that, couldn't we? Right? That makes sense? Okay. All right, so, but this is probably better, doing it this way. Okay, so we got all 3 of our x-intercepts. At which zeros does the graph of the function cross the x-axis? Based on multiplicities. Yeah. Negative 3 and 3, right? Everybody see that? Okay, good. Negative 3 and 3. Okay. So it does cross the x-axis, and it does so at negative 3 and positive 3. Okay. Are there any places where the graph bounces, where it touches the x-axis and turns around? Where? At 2. I guess that one's already, we can already see that one, can't we? It's at 2, because that was the multiplicity of 2. Okay. How would I find the y-intercept? Yeah, what happens at the y-intercept? X is 0. Right, so the y-intercept is just going to be f of 0, isn't it? Right, so if we find f of 0, well, what do we get from our function if we plug 0 in? We get 2 times 0 minus 2 is negative 2 squared, times 0 squared minus 9 is just negative 9. So I get 2 times 4 is 8 times negative 9 is just negative 72, right? I plug 0 in. Okay. Okay. Here's another way I could do that. I want to show you how these multiplicities. If I graphed, think of it this way. If I graphed the function x minus 2, y equals x minus 2, and if I were to graph that thing, what would it look like? Wouldn't it just look like a line with a slope of 1 and a y-intercept of negative 2? Everybody agree? So that's going to be a line that cuts through the x-axis at 2, right? Everybody get that? Because it's just a line. If I graph y equals x minus 2, it's a line. Now, what if I graph y equals x squared minus 9? Now, that's a parabola, But if I were to graph that function y equals x squared minus 9, I just want to show you how we could have done this without factoring x squared minus 9 any further. If I graph y equals x squared minus 9, what's that look like? Well, if I were to graph that, that's just a parabola that's been shifted down by 9, right? So there's the vertex, and it's just going to cross at -3 and +3. It's going to cross, it's going to cut through the x-axis at -3 and +3. Everybody see that? So there is another way you could have also reasoned your way through this without having to split it apart. Okay, we could have reasoned that when I solve this thing, I'm going to get plus or minus 3, and those are the two places where the parabola is going to cut through. Okay, does that make sense? Yes.
On the test, is like this going to be how it is like now, or is it going to be? Is it going to be mainly this stuff that we're doing now, or is it mainly going to be the exponent stuff we were doing before?
Oh, it's going to be kind of half and half.
Okay.
Yeah, kind of half and half. Yeah. Right, and then this one right here, if I did x minus 2 quantity squared, at 2, that's where the vertex of the parabola, this one has just been horizontally shifted by 2 to the right, hasn't it? Everybody see that? Right? That's what I wanted to say before I misspoke. So this one, if I were to graph what that one looks like, what does that look like? Well, over at x equals 2, we would have a parabola that just bounces off the x-axis, right? Okay. All right. Good enough. So let's graph this guy then. Okay, so we found we had x-intercepts. We wrote this as two times minus 2 squared, and then we factored it into x minus 3 times x plus 3. And we said our end behavior was positive even, right? Okay. So we got x-intercepts at positive 2, at positive 3. Whoops. Positive 3 is blue. And at -3. And our end behavior was this and this, right? So what's it do at the red x-intercept? Cut or bounce? Cut. What's it do at green? Bounce. What's it do at blue? So there it is. Okay. Make sense? All right. Last issue. Symmetry. Just want to introduce you guys to symmetry. Okay, so there's two kinds of symmetry we talk about at this point. Even symmetry, which is line symmetry, and odd symmetry, which is rotational. Now, we talked about this the other day a little bit, didn't we? Right? So you guys kind of, here are the pictures that we discussed. Even symmetry means folding symmetry about the y-axis, line symmetry. Odd symmetry means rotational symmetry about the origin, right? When does that happen? Well, there is a test for symmetry for both of these. The test for even symmetry is this. And this is really important that you know this, because even though there's a shortcut for polynomials for just we call it inspecting. You don't have to do anything. Just by inspection, you can look at the polynomial and tell what kind of symmetry it has. That kind of test doesn't exist for very many other functions. Usually in the future, if you've got some function and you want to know if it has even or odd symmetry, you have to subject it to this test. You evaluate the function at -x, and if the result is that it's equal to the original function, then that means it's even symmetry. If you evaluate the function at -x and you get the opposite, you get negative f of x, the opposite of the original function, it means it's odd symmetry. And if neither one of those things happens, there is no symmetry. Okay? So let's take an example. Like if I take this polynomial right here, f of x equals x squared plus 4, which is really the same thing as saying x squared plus 4x to the 0. we wouldn't write it that way, but there is an x to the 0 next to that 4, right? Okay, so now if I evaluate this at negative x, look what happens. Well, I'm going to substitute x for negative x. So I end up with f of negative x is the quantity negative x squared plus 4. Well, what is the quantity negative x squared? That's just x squared, isn't it? Because I'm going to have to square the negative 1, which makes it positive, and square the x. So I just get back x squared plus 4, which is my original function, right? So f of negative x ended up being the same thing as f of x, which means it's even symmetry. Okay, let's try another one. How about this guy over here? F of x equals x cubed minus 3x. Let's evaluate that function at negative x. I get the quantity negative x cubed minus 3 times the quantity negative x. What is the quantity negative x cubed? Negative x cubed, right? I got to cube the negative 1, which is negative 1, cube the x. Yeah, I just get negative x cubed. Minus 3 times negative x is plus 3x. If I factor out a negative 1, then that leaves me with a positive x cubed minus 3x. Well, what do you know? That's my original function, isn't it? So I got f of negative x equals negative my original f of x. Well, if that happens, if f of negative x is negative equal to negative f of x, that's odd symmetry. How could we have done this without even having to do the test for symmetry? Do you see a pattern? How could we have told that that blue polynomial was going to have even symmetry? Okay, all of the exponents were even, right? Every exponent was even. The red case, every exponent was odd because remember, x is the same thing as x to the 1, right? So we have kind of a cool rule here then. We know that polynomials with only even powers of x have even symmetry. Polynomials with exclusively odd powers of x are guaranteed to have odd symmetry. You don't even have to do the test. Now look what happens if we mix it though. What if we take a polynomial that has even and odd exponents and I subject it to the test for symmetry? So f of negative x is going to give me the quantity negative x squared plus 2 times the quantity negative x. Well, negative x quantity squared is just x squared, but 2 times negative x is minus 2x. So f of negative x is not equal to the original f of x, nor is it equal to the opposite, right? It's not equal to either one of those, and so there's no symmetry. So our shortcut then, we know that polynomials with both odd and even powers of x, it contaminates both symmetries and you get nothing. Okay? Make sense? All right. Why is this such a big deal? Because it makes it easy for us to graph stuff. Gosh, I wonder if I still have that up here. Do I have, like we just did a big example like this today in calculus where we did, this was pretty cool, where we used symmetry a bunch. This guy, check this out. So here's a problem we did in calculus today where we were looking at symmetry arguments on this one. And look, we were able to tell that this function had odd symmetry. So when we went to graph this thing, we knew that all I had to do, because it had odd symmetry, was graph the features of the function that from 0 to infinity, and then I could just reflect those around the origin to get the rest of the graph. So when I actually made my graph, all we had to do was graph this half of it and then just spin it around the x-axis to create the other half, right? That's kind of nice, okay? So we take advantage of this later on in math a lot. Okay, you may work.